Okay, I have installed the extension and I'm recording it. I hope it will record properly. So let us start with today's lecture. Most probably, Google has changed some setting, and we have to uh, change some setting. Most probably, from next class, it will work properly. So let's see. Today, we'll just continue with this screen recording. Okay. Let me change some brightness of my machine. Well, yeah. Okay. My voice is clear. Anyone, please confirm.
Yes, sir.
Okay. Okay. So last class we have discussed risk V architecture. We've started the discussion. We are discussing some initial architecture of risk V. So and the last class I said that from this list, this is the table, and from this table we'll try to understand all the instructions one by one. If it is not possible to explain all the instruction, but at least 70% of instruction mentioned in this table we'll discuss in this course. And once you understand all the instruction, then using those instruction you can write your programs. So I have to complete all these within next 2 3 lectures, because after that you will receive your assignments on assembly language programming. Okay. So last class I explained that how the if there is a small expression written in C, how can we convert it to assembly language code. First we assume that variables, and then we consider variables as register. Then I explain you that if registers are less, then how store some data in memory, and then first you load it, then perform the operation, and then after at the end of the operation you have to store the result back. So use of load instruction and store instruction also I have explained. And I also mentioned that what is called operand. So if we write an instruction like add x1 comma x2 comma x3, then this x1 x2 x3 are called operands, and this add is called opcode. So I think all this concept I have explained, so no need to discuss again. And then I explained this code where load and store was required, especially for interacting with memory. And see this the concept that I'm discussing, they are interconnected. So if you miss one lecture, then you have to read the book or watch my lecture before starting the next lecture. Otherwise it will be difficult for you to understand, and also uh, for me to explain. So last class I have explained about the add instruction, and or the arithmetic instruction like subtraction also I've explained. Today I'll start our discussion with this subsection, constant or immediate operand. So what is constant or immediate operand? So in most of the time, if we write a software or write a program in high level language, you will find this type of expressions many times. Means many time the operation that we perform, out of this operation is this one of the operand is variable and another is a constant. This type of expression is very common in programming language. And if you read the highlighted line here, it is written that when running the spec cpu 2006 benchmarks, you will find the constant operation. More than half of the arithmetic instruction have a constant operand. So now here the term of what is called spec CPU benchmark. So that I will explain later. And at this moment, when you will read the book, you can ignore this what is called spec CPU. But the meaning of this line is, if you write a application or any application or modern day application, when you convert those application in assembly language code, the instruction of those assembly language, almost half of them has a constant like this. So one variable and one constant. So how to perform these operations? Till now we only know a add operation like this, right? Add x1 comma x2 comma x3 means add the content of these two register and store it in the third register. So here you can see the two operands must be stored in registers. If that is the only instruction available, then how compiler will convert this code to assembly language code? First, it's not just that x will suppose x is assigned to a register called x22. With that, it is also required that this 5 is also need to assign either some memory or register. Suppose if it is assigned a register called x20, then it is fine. Otherwise, another option is this constant maybe need when the compiler will store this constant in memory, and before performing the addition, we have to load the constant from memory to the register. For example, you can see they assume the second case here. Suppose that compiler will store the constant in a memory, and this load instruction is loading the constant from memory and storing it in x9 register, and then we are performing the addition, assuming that x variable is stored in assigned with x22, the whatever I have mentioned here. So these are the alternative, but they are not effective, are not very effective or efficient. Why? Because as it is written here that almost half of the instruction has a constant, and if every time for each constant, if the constant part is mentioned in memory, then what we have to do, we have to go to memory and fetch the data. So going to memory and fetching it data is a time consuming process, right? So that's why the alternative is to use another type of instructions, and those instructions, the constant part is embedded within the instructions. So you can see an instruction here. Let me write the instruction here. Add I, this is called add immediate, then x22, this is the destination, no problem. uh, and then I can write 4 here. So you can the difference with these and the previous instruction was add, suppose x22, x22 and x9. So this was the previous instruction. Here both operands are register. Here one operand is register, another operand is constant. So this is called immediate instruction. This immediate instruction is very very helpful when you will design assembly language, when you will write assembly language program. So this 4, you can see this 4 is written within the instruction. Within the instruction 4 is written. It's not like that. To this 4, for this 4 you have to go to memory and fetch the data. So you can, if you read here, you can you'll see by including constant inside a arithmetic instruction, operations are much faster and use less energy. So there are two. Why operations are much faster here, that I have already explained, because you no need to go to memory and fetch the data. Data is already within the instructions. So the fetching time or interacting time with memory, interaction time with the memory will be saved. So your operation will be faster. This is the first point. And why they said energy, less energy? Because this energy part I have not discussed in this course, because it's a high level concept. Honestly, we may skip this part also here, but quickly I'll explain that energy means whenever you are running a computer, right? Or maybe if you are running a laptop. So if it is running on battery, then after some time battery will be discharged, right? So so it depend on, if you are not doing anything on laptop but laptop is on, then the battery will last longer. But if you are doing some heavy operation, you are watching some movie, or you are watching some, you are playing some game, then it will take it will discharge faster, right? Why? Because if more operation you will perform on the computer, it will consume more energy. Okay, and if you do less operation, then it will consume less energy. So here if we need to go to memory for this, then when you'll go to memory, then you are interacting with memory, so obviously latency will be high. And since you are interacting with memory, memory also need to supply. So at that time, the since memory is also need to access, then energy consumption will be more. Means you are, so in today's world, whenever we are designing a computer, then performance is not the only issue. People, as a researcher, we are also trying to, every day we are trying to how to reduce the energy consumption of a computer every day. So reducing energy consumption is a challenge. So if there is any opportunity is there by using which we can reduce the energy consumption, then we'll always go for it, because you know how important the energy consumption is today. Okay, so I'll not discuss this point here anymore, because energy consumption and all, how to reduce energy consumption, this is not directly connected with this code. Those are advanced level concept. Yes, the videos that I share of advanced level videos, the or extra lectures, and those lectures maybe I'll explain. But remember, those lectures are not directly connected with your course. So I hope the advantage of constant immediate instructions are clear. So immediate instructions are not for just add. Immediate instruction is also possible for sub. Suppose I can write sub I x2 x3 comma x comma 5. The meaning of this line is x2 equal to x5 minus 5. Okay, so if I go to the table, let me go to the table. Yes, listing. Okay, so immediate instructions will be written, data transfer logical. See, the third one is add immediate. It's the immediate instruction. The third one, add immediate, is the immediate instruction. There will be some load immediate. There are some other immediate instruction also, but here only add immediate is given. So subtract immediate is also possible. You can also use that. Okay, so immediate instruction is clear. Now after this, all this, I'm skipping these points. You can read it once if you want. Then the next point here is sign and unsigned numbers. So before starting this section, I'll not discuss in detail because I'm assuming that all of you know have the basic concept of these three: binary numbers, digital numbers, and decimal numbers and hexadecimal number. Means if there is a decimal number given, how to convert it to binary, or a binary number is given, how to convert it to a decimal number. This concept you already know. And also what is called hexadecimal number, how to convert a binary to a hexadecimal or hexadecimal to binary. Those things, those concepts you already know, that I'm assuming. If these concepts are not clear, then let me know. I can share some videos where you have to clear those concepts, but this I'm considering as prerequisite for this course. So those lectures won't be considered as a part of this course. Okay, so here quickly I'll explain the purpose of this section here, that sign and unsigned number, mainly how computer represent those numbers. We know that a computer only understand binary, means 0 and 1, but how we represent a signed integer or an unsigned integer or any other signed numbers and unsigned numbers, how those numbers are representing by a computer, that we'll understand here. So for this, let me share a whiteboard here. And as I said, I'm assuming that you know this concept: binary, decimal, and hexadecimal. These concepts you already know, but quickly I'm explaining whatever required for this course. Suppose we have a decimal number 4. So if we convert it to binary, we write it normally in this format, right? 100. So if we have a number like 5, then the corresponding binary number is 101, right? So here, since we are discussing about double word, we said every time computer will either request for a word or a double word, right? So I said the word is double word is a 64 byte of length. So normally here we'll assume that every number is of 64 bits long. So every number is of 64-bit long. So now if you see this number 4, when we convert 4 to binary, it's only taking 3 bits, right? 100. So what about the other left bits? Those will be filled with 00000. All will be 000. The same thing here. If as we are saying that every number will represent here with 64 bits, then only the last 3 bit here will be 101 and other bits will be 00000. Okay, so this is called least significant bit, and this is called most significant bit. So this is how we can represent it. If we are going with 64 bits, if we go with suppose instead of 64 bits, suppose we want to go with only 10 bits, then on also last three will be least significant 3 bit will be 100, and remaining bits will be filled with 0. The same thing will be here also. So I hope you are understanding that if we need if the number of bits available to store is more than the bits required here, then those leftmost bits will be filled up by zeros. So up to this point it is clear. Now the problem here is with a negative, with a signed numbers, because here I have not mentioned about these numbers are positive or negative. So so if there is a sign bit is there, then suppose how to represent -4 and how to represent -5. So if we are going for sign number, then one obvious way is just use or reserve the most significant bit as sign. Means most significant bit is 0 means plus, and most significant bit 1 means minus. So in this case, we can represent -4 as 100 is for 4, right? And one more bit is required here. Minus means 1, right? So for minus I need one bit here. So minus 5 also, 101 is 5, and one bit is required here. So this is for negative numbers, and for plus 4 and plus 5 we will write 010, and we'll write 0101. So you can see that for one bit is we need to reserve for sign here. So suppose we have instead of 64 bit, we only 4 bits are available. We need to store all the numbers in 4-bit format, suppose. So what is the minimum value we can store here is 0000, and maximum value we can store here is 111. So if we go for unsigned way, then this is 0, and this we can consider as 15. So 0 to 15 we can store here. But if we want to go with signed values, then how many bits? Because here this last bit will be stored for sign, right? Either 0 or 1. 0 means positive, 1 means negative. So after this only 3 bits are remaining here for number. So with this 3 bit we can represent what? 000 means 0, and 111 means 7. So 2 to the power minus 2 to the power 3 sorry, minus 7 to plus 7. Only these number can be represented with these 4 bits. Though there are to represent 7 we need only 3 bits, but minus and plus this sign bit need one bit here. So these 1 bits will be required for sign. But now let us do one calculation. Suppose what we can do is we want to add two numbers, suppose plus 4 and plus 5. So result is plus 9, right? So plus 4 can be represented with this 4 bit, isn't it? Because it is within this range, minus 7 to plus 7. Plus 5 is also from this range, so minus 7 to plus 7. So suppose your hardware requirement is this, you can store only 4 bit. For you can give only 4 bit to each number. So using this 4 bit, you can represent 4, no problem. You can represent 5, no problem. So there will be two values here. One is this 4, and maybe one more box here which is representing your 5. Okay, now after adding your result is 9. Can you store result 9 with these 4 bits? It's not possible, because if your one hardware component is only of 4 bits, then using this 4 bit you cannot represent 9, because if you want to represent 9 you need more bits. So that is called an overflow. So how to handle overflow and all, we also discussed this. So you, yeah, at this moment you just try to understand what is called overflow. Overflow means if we just think about the numbers, there will be no overflow. But if we try to relate a number with a hardware means component or a storage, where we need to and how we want to represent, here you can see only 4 bits are reserved to represent a number. In that case there will be a restriction is minus 7 to plus 7. In this case plus 4 you can represent, plus 5 you can represent, but after adding the result plus 9 you cannot represent, you cannot store, there will be overflow. So that concept of overflow maybe you need to understand. We will discuss it in more detail in future also. So overflow ho gaya. Now uh, so now another problem here is there is one problem that I'm saying, that use the most significant bit. This is the leftmost bit as a signal, as a sign value, either 0 and 1. So but if we go with this solution, there are some problem. And if we let us go to the book. So first they have explained, see I'm scrolling this section. So if I scroll this section, there are this type of explanation given. I'm ignoring this. Why I'm ignoring this? Here they've explained that they discussed the formulas, how to convert a binary to decimal to binary. I think these points you already know, so it is your responsibility to read and understand. I'm only explaining what is important. See, I've explained what is called least significant bit, what is called most significant bit, that I have explained. And then I have explained now I'm discussing about this, that why the format that I'm saying, that last most significant bit or leftmost bit, when we use for sign, what are the problem? The one obvious problem is how you will distinguish between plus 0 and minus 0. Because plus 0 means you will write, you have to use 0 for the plus, and minus means you have to use minus. So how you will represent 0? So there are two representation possible for 0. in this format. So this is a problem. This is not a big this is actually a problem when we design a computer. This is and there are some other problems also, because if we put this sign, then the actual additional module that, or the adder module that we say, it is difficult for them to, first of all they have to trace whether the value is positive or negative. So it's a, we can say again, the latency will be more or energy consumption will be more. So that's why this is not a good solution, and people are nowadays not using this solution that will use the most significant bit for storing the sign. So this is not, so the solution that people use nowadays is called two's complement format. So actually the numbers, the negative numbers are represented as two's complement format. And in two's complement format, what we say that leading 0 means positive value and leading 1 means negative value. So let me explain this two's complement format in more detail. So I will discuss here the two's complement format again. First, without understanding much about what is called what is how to represent positive and negative, just let us try to understand how to what is called two's complement format. Suppose this is 4, and 4 is represented by 100. Then the two's complement of 4 will be, two's complement of 4 will be, you have to convert, how to calculate two's complement. First you have to flip all the bits. So 100 means 0 1 1, and then you have to add 1. So it will be 1 plus 1 0, then 1 plus 1 0, and then 1 this. So two's complement of 100, that is 4, is again 100. How we are calculating two's complement from? To calculate two's complement, first of all you have to flip the all the bits here. So we have flipped all the bits, means 100 becomes 0 1 1, and you have to add 1. So after adding 1, you are again getting 100. That is two's complement of 4. So now if we go for 5, then it is 101. So if we go for two's complement here, then we have to flip all the bits 0 1 0, and then we have to go for plus 1. Plus 1 means 0 1 1, then 1 0 1. So this is the two's complement. This is the two's complement of 5. So this is there is a shortcut also for calculating two's complement. If I ignore this, or if I ignore this, so just checking this, you can also calculate two's complement. So for this, what you have to do, you have to flip the bits, start flipping the bits from the leftmost position, and keep flipping until you receive the first one. Oh no, so now sorry, Cliff, you have to keep flipping the bits until you receive the last one. So the moment you receive the last one, don't flip anymore. So here you can see there is no now assume that there are instead of 3, we are representing this value with 5 bits. So how we'll calculate complement from here? Keep flipping the bits, 1 1, and I said stop when you will reach the last one. So the moment you reach last one, so will not flip this bit and will not flip anymore. So this will be the two's complement. Here suppose for 5, I am ignoring all this and I'm trying to calculate the two's complement of 5. What I'll do, I said I will keep flipping the bits until I reach the last one. So I'll keep flipping the bits. So first will be 1 will be 0, 0 will be 1, and the last, the moment I reach the last one, I'll not flip that, and I'll, so the value will be 0 1 1. See, so this, in short, you can calculate a two's complement in this format, that you have to, from leftmost bit or the most significant bit, you keep flipping the bits until you reach the last one. The moment you reach last one, don't flip that bit and don't continue flipping. So this is a shortcut way to calculate two's complement. So now let us go with some more detail. Now let me think that all the values here are not representing with 5 bits. Suppose here I'm say, let us consider the 4 is representing with 16 or 32 bits. Suppose this is a 32-bit box. Suppose a 32-bit. So yeah, we are representing 4 with 32 bits. So how will represent? Last 3 values will be 0 0, and all values here will be 0 0 0. Maybe I am writing less 0, but you have assumed that there are 32 bits. So all the leftmost bits are now zeros. So if this is your 4, how can we calculate two's complement? As I said, we'll start. Suppose this is another box. Here I have to store the two's complement of 4. Again, 32 bits are there. So what I'll do, I'll keep flipping all the bits 1 1 1 1 1 until I reach the last one. The moment I reach last one, I'll not do anything from here. everything will be there. So you can see the 2's complement of 4 is same. So when I was discussing about only 3 bit, I said 2's complement of when I was not discussing this, I only said that 4 is 100, and I calculated that 2's complement of 4 is 100 is same. So here you can see these bits are extra bits, right? If you have extra bits, then all extra bits will be converted to 1 here in 2's complement. So as I said, if this is your plus 4, then this is your minus 4. Normally, as I said, the negative numbers are represented with 2's complement, 2's complement of that number. So in computer, if we write 4, they will store this value. And if there is a restriction of 32 bit, then they will store this value 000, and then last 3 will be 100. If you try to, if you want to store minus 4, they will store this bit combination in the memory of this 32 bit. All are 111, and last 3 will be 100. This is plus 4 and minus 4. This is how they differentiate it. If you understand this part, then remaining thing will be easy for me to understand, explain you. So you have to understand from this point then what is 2's complement and how to calculate a 2's complement. Let me calculate for 5 also. Suppose this is 5, and here if I assume again 32-bit box, so you have to fit everything here. Then last 3 digit will be 101, and remaining will be all 00000. This is your plus 5. If we want to represent minus 5, then we will represent it, you can represent it in 2's complement format. So how can we calculate 2's complement format? Let us consider that I'll store it in another 32-bit box. So I'll start from this. I'll flip 1 1 1 1 until I'll flip this also. I'll flip this, then 1, until I reach the last one. Last one is the most significant bit. So I'll not flip the last one. I'll not flip the last one. Before that, you can see from after I have flipped all this bit here. You can check here. All these bits are flipped. The last one I have not flipped. So this is the if this is plus 5, this is minus 5. Okay. So now let us go back to the chapter. So if you go to this chapter, they have, instead of 32, they have used 64. So you can see these values, you can see very long values, right? So you have to understand these as a box like, and this box is of 64 bits. This is how they have explained all the numbers here. Also, see how you can represent 0 here. See or how you can represent 1. Just concentrate here. See, 0 1 means this is a decimal 0. 1 10 means decimal. So in decimal 1 you can represent it binary as 0 1. The decimal 2 you can represent as 1 2 or 1 0, right? Means 1 we represent as 0 1, 2 we represent in binary as 1 0, 3 we represent as 1 1, 4 we represent as 1 0 0, right? So to represent 2 in decimal, we only need 2 bits, right? 1 0. But since every number we have to fit in a fixed value here, 64 bits, so all the leftmost bits will be 0 0 0 0 here. See, all the leftmost bits here are 0 0 0. So don't be confused. Okay, so here the restriction is we have to store every number in 64-bit format. If the restriction is 128, then there will be more 0 in left side. If it is a 32-bit format, then there will be less zeros in left side, but calculation will be same. So now concentrate on this two. Let me remove all these things. Concentrate on this line, concentrate on this line, and concentrate on this line. If this is plus 2, and then they have calculated minus 2 using this, how? Same I said, if this is plus 2 stored in a 64-bit box, then if you want to convert it, and if you want to store a minus 2, then you have to convert it into 2's complement form. So this, let's see how they have converted into 2's complement form. You can easily convert it, right? What you will do, will start from the leftmost position here, from this position, and I'll start flipping all the bits, right? We'll start flipping all the bits from here. 1 1 1 1 1 1, I'll flip, and when I'll stop flipping, the moment I'll reach the last one. So last one is this one. So the moment I'll receive the last one, I'll not flip. So you will get this one. Keep flipping until I receive last one. I'll not flip anymore. So here you can see this, if this is the plus 2, then this is your minus 2. This is how we represent negative number in computer, specifically in risk B architecture. So I'll not explain all these formulas in more detail. If whatever concept I said, how to calculate 2's complement, and how negative numbers are stored in 2's complement format, you, if you understand this part, then it is enough. And on top of that, you have to understand what is called overflow. if you have a restriction of, suppose as I said, 64-bit, and if you are adding two numbers and the result is not possible to represent in within 64-bit, then that we call as overflow. So whenever we are this architecture that we mentioned, that add instructions, suppose, right? So if those instruction when we implement in RISC-V architecture, there are by default there are mechanism which can detect that if there is a overflow or not. If there is a overflow, then it will give you a warning that see there is a overflow. So I'm not going to explain all these examples, and I'll try to understand those examples by yourself. If any point is not clear, then please let me know. What I'll do, I'll share some introductory lectures where the concept of binary, decimal, hexadecimals are explained in more detail. Even after that, if any point is not clear, then please let me know. Okay, I'm skipping this hardware and software interface. I'll come back again here. This point is important, but I'm skipping. With skipping this, I'm going directly to this example, negation shortcut. Negation shortcut means we know what is 2, right? So suppose 2 and minus 2 is there, so minus of minus 2 is 2 again, right? Minus of minus 2 is 2 again. So they proved it. Suppose they said if 2 can be represented with this binary, if you are representing 2, then first they calculated minus 2 from it. So how to calculate minus 2? So first they go with the in longer explanation that I said. First they will flip all the bits, and then they are adding 1, so ultimately they are getting this. The shortcut you already know, I said. Now they keep flipping the bits until you reach the last one, so ultimately they are getting this. So they are saying this is minus 2. So how can you confirm that this binary bit pattern that you get, this binary bit pattern is representing minus 2? How can you be sure? To make it sure, if this is a number, and what about the minus of this number? If this is minus 2, and if we again go with minus of this this value, then we should get 2, right? Minus of minus 2 is 2. So assuming consider this number, now try to get 2's complement of this again. So how will get 2's complement of this number again? Again the policy is simple. Will go to shortcut, will not go to their technique. Their technique is replace flip everything and then plus 1. Will not go with this technique. We'll just flip all the bits. Will keep on flipping until we reach the last bit here. So 0 0 0 0 0 0 0, everything will be same, and only the last 1 0 will be there. So this is the 1 0 in the last two bit, and all other leftmost bits 0 means it is 2. So this is correct, right? So this is not a big example, just they cross check that two's, if you represent negative number as two's complement, it is correct or not. Yes, it is correct, because you can represent a negative number in two's complement, because if we go again a negative of this, if you again try to calculate two's complement of this number, you will get the positive number. Okay, so this part is done. Then I'll go back to this point that I skipped, hardware and software interface. Here you can see there is a term called sign extension. Sign extension, this point is important. Why? Suppose you have a number here, and number is a suppose it's a positive number, 0 0 0 0 0. Suppose it's a 32-bit number. I'm not using all the 32 bits here. Last two bits are 1 0 0. So which number it is representing? It is representing plus 4, right? 32-bit. So now I want to store this number, this 4, in a larger register or larger storage. Suppose this storage is of 64-bit storage. So I want to move this number, that is 0 0 0 and 1 0 0, there, which is representing as 4 plus 4, sorry. I want to copy this number from this box, that is 32-bit box, to a 64-bit box. Normally I'm actually mentioning here as memory space or register, I'm just saying box. So that is, I can simply do this 0 0 0 0 0 up to this part, half part. This half is 32-bit, right? What about this left half? What about this left half? So if it is a positive number, or if it is an unsigned number, I will simply load all this left as 0 0 0. This is called sign extension. But if it is a negative number means, suppose here it was a 1 1 1 1 1 1 1 1 0. What is this? This is actually in this box now minus 2 is stored, right? Minus 2 is stored in 2's complement form. So now if this is minus 2, how can we move this value to a 64-bit part? 64 bit, this is the half. Now this is the, so 101111, this will be stored in the first 32 bit half. That is fine. Right side. What about the left half? In left half we have to copy the sign bit. The sign bit will be extend. So this is called sign extension, and this is important. This is important because many time we'll use it, that we'll copy or we'll collect a data which is suppose a 32-bit data or even less size data, and we have to put it in a 64-bit location. Normally all the register that I've explained, x0, x1, x2, they are 32 or 64-bit of length, right? I have explained it. So now suppose if you want to store a byte to this register, then how you'll store it? If the byte is unsigned, then we'll store it in the leftmost part, and all in the rightmost part, and all the leftmost bit will be filled with zeros. It is explained here, right? And if the data, the byte that I want to store in this location, it's a sign byte, then we have to copy the sign bit in this format. So there are two more instruction available in RISC-V. One is called load unsigned, load byte unsigned, and load byte. So last class I explained load with LD, right? LD means load double word. Understand what is called double word? Means you will go to memory, read a 64-bit content, and you will copy it to a register. No problem with it, because 64 you are copying to 64. Sign extension is not required. But here with LB, what you are saying, you are going to memory, loading a 1 byte of information, and now you want to store this 1 byte of information in a 64-byte register. In that case you need sign extension. But if you are loading a unsigned, so LBU means load byte unsigned. So if we are going with load byte unsigned instruction, then you will go to memory, load 1 byte, and you will directly store it in a 64-bit register, and all the leftmost bit will be replaced with zero, because it's unsigned number, all will be zero. But if we go with load byte, then we'll assume that it's a sign bit. So sign bit extension I've already explained. If it's a 2 bit, then all the 1 will be copied here. If it is plus 4, then all zeros will be copied. So the same concept is written here. And now if I again go to this list, ISA list, you will see there are a lot of load instruction. You can see load double word that I have used, LD. Then you will also see a load byte. See here, load byte, LB is there, LBU is there. So these load byte, suppose sometime you no need to load the entire double word. If you only want to load a single byte, then you can use load byte or load byte unsigned. Okay, so I think sign extension is clear. There is an example also given here for sign extension. I will not explain it. I think I have already explained the concept. You have to understand this concept. So from this section, that is sign and unsigned section, what is required for this course? The requirement of this course is you should know the concept of binary, decimal, and hexadecimal numbers. How to convert one format to another format, that you have to that you should know as a prerequisite. And then today I've explained how to store a positive number in computer, how to store a negative number in computer, and we normally go with two's complement format. And these two's complement format will use throughout this course. So you should understand whatever I explained today, or if you, even if you read the book, you'll understand it, that positive number, if plus 2, how to store plus 2, and how to store minus 2 after converting it in two's complement format. So all this part if you understand, then this section is enough. And on top of that, you have to also need to understand what is called sign extension. See the summary in last point. It is if you read there, the main point of this section is that we need to represent both positive and negative integers within a computer. And although there are pros and cons to any option, the most important choice that we go is two's complement format, still 1965. This is mostly used, almost all the computer use tools complement format to represent sign numbers till 1965. But yes, there is still a question, means how about the, what about the floating point values? You are only saying about integers. So that will not discuss now. Maybe after the end sem, after the mid sem, we will discuss how computer represents the floating point values. Because why I'm not discussing here, because it's a complicated thing, and that's why the book also not explaining the floating point part here. So this section is done. You check whatever written here, check yourself. You should try to solve it by yourself. I am not explaining it. At the end there is a concept also written about one's complement. If you want, you can read it also, one's complement. I am not for this course, only two's complement is important, that already I have explained. And then we'll go with 2.5, which is again very important for this course. So 2.3 is important. 2.4, when I was explaining sign and unsign, I said it is not very important. Only if you know few concepts, then that will be enough from 2.4. But from 2.5, again, this is directly connected with this course, and it is very important. So representing instruction of a computer. So I'll start this section today, and I'll complete it in next class. Representing instruction means, suppose the instruction that I have written, add x1 x2 x3, or if I write another instruction like sub x3 x5 x6, and add I also I have explained, right? X1, suppose x2, and then here I'll write x8. Then if I write a load instruction, that also I have explained in lecture. So these instructions that I write, all in risk view, we assume that every instruction takes 32 bits. So suppose again, you have to assume that you have a 32-bit block box, suppose, and within the box you have to fit all the instructions, whether it is add instruction, sub instruction, or load instruction, or any instruction that was available in that table that I'm showing every time, right? In that table, whatever instructions are there, or any of these instruction will fit in this in a 32-bit box. Okay, so now any instruction, whatever instruction you can mention, it's a combination of binary bits, right? 1 0 0 1 1. This will be just a combination of binary bits here. So now suppose you need to execute this four instruction one by one. So first time when computer will fetch add instruction, it will fetch a 32-bit binary value. How it will understand that okay, it's a add instruction? Because till when because first of all, if you remember, I said decode phase. After fetch there is a decode phase. In decode phase, computer understand that okay, it's a add instruction. But if everything is just a binary thing, a combination of binary values of 0 and 1, there should be some mechanism, right? Based on which computer should understand that okay, it's a add instruction, or it's a subtraction instruction, or add, even after add, what about this register, which are the source register, which are the destination register. So these must, should be some standard representation based on which computer can understand during the decode phase that okay, this is a add instruction, or these are the source registers, and these are the destination registers. So all these things we will discuss in this section. So before going all the detail, uh, concentrate on this add instruction, add x9 comma x20 comma x21. So here what this x9 is actually called destination register. We'll call it as RD, destination register, and these two are source register. So you can say this is rs1, this is rs2. Source 1 and source 2, these are terms you have to remember throughout this course, that what is called destination register, what is called source 1, what is called source 2. So suppose this is your 32-bit box, and in 32-bit box you have to represent this add instruction. And as I said, everything is in binary. So today I will not discuss it in binary. Let us discuss it in hexadecimal, because sorry, in decimal, every binary number has a corresponding decimal number, right? So just instead of going with 100, I'll go with 4 today. Ultimately the thing is same, right? So here, to represent this add in this 32-bit box, this 32-bit box is divided into multiple field. So you can see there are five field. If you say this is 1 2 3 4 5 and 6, there are six field. So out of this six field, this field, that is sixth, and then fourth, and I think this first, these three fields are representing the opcode. What is opcode? This add is called opcode, right? This is called opcode of the instruction. And this x9, the rd, rs1, rs2 are called the operands. Opcode and operand, these are called operand. Operand I have already explained, right? Or here the add is called opcode. So these four these three values I will jointly represent. I will say that okay, this is a add instruction. Means for this you have to store 51 here and 0 0. If we based on this is, so when you wrote this instruction, first computer will check what is in this means in first, fourth, and sixth field. Based on this, it will decide okay, it's a add instruction. After this, what are the remaining three parts? There are RD, RS1, and RS2. So RD is stored here. See, what is RD? RD is X9. So register number 9 is stored here. This is for RD here. And where if you see, RS1 is stored in RS1 is X20. So here this is for RS1, and this 21 is for RS2. So there are fixed locations. So in this, and for all this field, the number of bit is reserved. Means number of bit is already, means I think if I go down, see, here there are 7 bits, 5 bits, 3 bits, 5 bits, 5 bits, and 7 bits are reserved for each this field. So number of bits are reserved for each this field, for each field, and based on this fixed bits, we represent that what is the opcode first, and after deciding the opcode, we can also decide what is the means source and destination registers. So this is not the end. There are more challenges, and better I should stop here because I cannot complete this section. But before stopping, let me show you a figure. This figure is given in this book, but at the, I mean, in this chapter, but the end of this chapter. So you can see, if there is a add instruction, okay, I cannot write here. So if this is the add instruction, then the opcode field, this is the, and there are three field. Okay, I have missed one thing, otherwise you will not understand. Let me delete all this thing, and then I'll write a let us say this field as opcode, and this field as function 3, and this last field as function 7. Okay, opcode, function 3, and function 7, combining these three, we computer understand the opcode of a instruction. So now if you'll go to this diagram again, see, for add, opcode is 011001, which is actually 51 written in decimal, and in function 3 you need 0, in function 6 or function 7 you need 0. So function 6 I have not explained yet, so you can consider it as function 7 in 7. So same, if you want to go for subtraction operation, then again in opcode field you will write 51 only. In function 3 you will write 0, but in function 7 you will write 0 1 0 0 0. This binary bit you have to write there. If we go for some other instruction, suppose a AND instruction, I have that instruction I have not explained in this class. For that instruction, what, how will represent? So in opcode field we will again write 51, and in function 3 field we need to write 111, that is 7, and in function 6 field we need to write 0 0 0 again. So in this way you can represent any instruction by using this format. So but there are still limitations, and there are a lot of things need to discuss here. That's why I'll start again from this section tomorrow. But before starting this tomorrow's lecture, you can read the chapter once, at least the initial 2 3 pages, so that it will be easy for you when I'll start the next lecture. So I'm stopping my lecture here. So if you have any queries, you can ask. Just 1 minute. Sir, can you please 1 minute? Can you please give the instruction for tomorrow's class test? Instructions for tomorrow's classes. See, the generic instructions I have already shared with all of you. So again, I'm repeating. So until the course is going in online mode, all the quizzes, all the class tests will be only for objective questions will be there. There will be no subjective questions, and yes, there will be negative marking also. And you have to answer. You only answer if you are you are completely sure. Otherwise, don't answer that question. Okay, and syllabus will be whatever I discussed till last week. Whatever concept I have discussed till last week will be added, excluding those extra lectures. Whatever extra lecture I am sharing, don't think that those will be covered in your course. If you are interested, then only you watch those lectures. Okay, so any other information you want about the class test? Yes, 6 p.m. At sharp 6 p.m. you will get a link, so keep checking the your email gmail inbox. And I'll not share the link in Google Classroom. I'll send, each of you will receive a email from my side, and in that email the link of your quiz will be there, and the quiz will be in a Google form. So you have to click that link and you have to you have to answer the quiz. And please remember that I'll strictly follow the submission time. There will be, I'll not stop receiving the responses. If for example, suppose the deadline is at 7 p.m., suppose, you can still submit your answer at 8 also, there will be no restrictions. But later I'll check the timestamp, and based on timestamp, if you submitted late, then I'll reject your submission. So make sure that you are submitting on time. I'll check the timestamp later. Yes, I have already answered that. Test will be in Google form. Any other queries? Last still lecture 7. Yes, last week of Friday it was lecture 7. Means lectures will be till last week Friday. I forgot it was lecture 7 or lecture 8. So whatever I've discussed till last Friday, it is included in this class test. Okay, so since it is already 3, I'm stopping here. Thank you for watching.